So today we're doing experiment 10, and with this experiment you don't actually use any chemicals in the lab. You simply do and work on the worksheets that are in your lab manual. So what we're going to do is we're going to work through several of these examples given in the worksheets for experiment 10. And with these examples, one of the things that you have to be able to do is generate a correct Lewis structure. You also have to be able to make a 3D model, which when you're in lab, you'll actually build some of these models so that you can see what they look like in 3 dimensions. And you also need to remind yourself about the bond angle, because all of these things are very important, especially with chemical reactivity. So what we're going to do for experiment 10 is we are going to work through some of the problems given in the worksheets. So the first one that I'd like to look at is BF2. So if we're asked to generate a Lewis structure for BF2, the first thing that we have to do, and the first step in any Lewis structure, is to determine the total number of valence electrons in the molecule. And if you recall, the number of valence electrons is equal to the group number. So what do I mean by that? Well, beryllium is in group 2. So beryllium, there are one of them, has 2 valence electrons. So we include that in our tally. If we look at fluorine, there are 2 of them, and fluorine is in group 7. So each fluorine has 7 valence electrons. So we go through 2 plus 14. So in total, we should have 16 valence electrons drawn. So 16 dots in our Lewis structure. And this first step here is also one of the things that you will use to double check to make sure that you've drawn your Lewis structure correctly. Now, the second step in any Lewis structure is to determine what your skeletal structure looks like. Basically, what is bonded to what. And most of the time, the central atom is written first. So in this case, that happens to hold true, where beryllium is the central atom surrounded by the fluorine atoms. Now, the only exception to that is when you have an acid. So say, for example, you have H2SO4. Although hydrogen is written first, it will never be a central atom. So keep that in mind as you're going through acids. Hydrogen is never going to be the central atom. But in this instance, we don't have a hydrogen, so we know that the central atom is typically written first, and in fact, for this particular example, it is. So that's step 2. Step 3, we need to draw single bonds from our central atom to our terminal atom. Now, the fluorines in this instance are the terminal atoms. So I need to draw a single bond from my beryllium to each of my fluorines. And you can do this in one of 2 ways, depending upon what your instructor prefers. You can draw 2 dots, which signify a single bond, or you can draw a straight line, which also signifies a single bond. So either way, you can choose to draw a bond from your central beryllium to your terminal fluorines. But I will say that you should be consistent throughout. So for our purposes, I'm going to show you with lines. So I will change this to a line, even though a single line in Lewis structures is equivalent to 2 dots. Okay, so step 3 is completed for our Lewis structure. The next step is to give our terminal atoms an octet. So fluorines are the terminal atoms. And I have to think about what are some of the exceptions. What things don't want an octet, meaning what things don't want 8. And if I recall, I remember that hydrogen doesn't want 8. It only wants 2 valence electrons. We have beryllium. It doesn't want 8. It only wants 4. And we have boron. It doesn't want 8. It wants 6 instead. Now, fluorines are none of these exceptions. So what that means is that you need to draw fluorine having 8 electrons around it. Now we've already have 2 electrons drawn right here in our single bond. So we need to give each fluorine an additional 6 electrons, and we need to draw them as pairs. So you can draw them as dots or you can draw them as straight lines. But again, it depends on the preference of your instructor, and whichever way you choose, make sure that you are consistent. So I'm going to use the dots when drawing the electrons, the lone pairs. So I draw 3 additional lone pairs, which indicate that each fluorine now have 8 valence electrons apiece. So that is the 4th step in any Lewis structure. Doesn't matter what it is, this is what you're going to do. So once you've done that, then you say, okay, how many valence electrons have I drawn in total? And what I see is that I've drawn a total of 16 valence electrons. And I go back to the count that I should have. I should have a total of 16 valence electrons. So you think, okay, I have 16 valence electrons, I've drawn all 16, you need to check, does everything have an octet? Well, you know that fluorines both have an octet, but does beryllium? And we look and see that beryllium only has 4 electrons around it. It's got 1, 2, 3, and 4, because remember, in covalent compounds, the electrons are attracted to both nuclei, so they are sharing, so we count them for both. So beryllium only has 4, which is not 8. So you think, oh, beryllium does not have an octet. But remember, beryllium is an exception to the octet rule. Beryllium only wants 4 valence electrons, and right now it has 4 valence electrons, so it has an octet. So we look and we see every element in our structure has an octet, and we've used all 16 of our dots. So this is the correct Lewis structure for BeF2. Now, we then have to use this to generate a 3D model. And when we have a 3D model, when we're asked to draw one, the thing that we need to pay attention to is the central atom. We have to look at the central atom and say, how many regions of electron density are around this central atom? So that could be lone pairs, that could be bonding electrons. Now in this particular case, we see that around beryllium, it has 2 bonding pairs, or 4 electrons. So when we think that we have 2 bonding pairs, we've determined this. Then we think about the different shapes that are available to us when we think about 3D models. And when we have 2 regions of electron density around our central atom, we know that that falls into the category of linear geometry. And how do we draw this in 2 dimensions? Well, when we're drawing 3D models on a 2D piece of paper, for these, we have our central atom, we draw our bond, and we include our terminal atoms. Now, any lone pairs on your central atom you need to include, but in this case, they don't have any lone pairs on the central atom, so we don't have to worry about that. You do not have to include lone pairs on the terminal atom, so you do not have to draw those 3 additional lone pairs on your fluorine. So you show this having this linear geometry, and what do I mean by that is that we want these fluorines as far away from each other as they can get. And in order to do that, the farthest they can get away from each other is 180 degrees apart. So you have to represent that in 2 dimensions as best as you can. So we know that our bond angle is 180 degrees. It has linear geometry. We would draw it, beryllium, with 2 single bonds to the fluorine, and I'm showing them 180 degrees apart. So this is our 3D model of BeF2. This is our Lewis structure of BeF2, and we have the name of the geometry and also the bond angle.